we're going to get through kind of like the middle of chapter 27, which is not on the screen here somehow. So let's wait for that. Okay, there we go. Sorry about that. I just didn't plug it in properly. It's like what I do with a lot of my friends. Okay, so last time we talked about this idea of, let's say if this was, you have a bunch of wires here actually, right? When you want power to go through things, or even not just power, but like information is carried this way in your devices also. You want electrons to be moving around. We have this thing called current, right? Specifically, we're going to talk about this thing called the electron current so far, right? And this is just how many electrons, the number of electrons, right? Actually, the book used capital NE, are moving through a wire per unit of time. Okay, and we call that lowercase ie. Okay, we're going to see why this is going to be a lowercase thing. And then we did a couple of geometry thing where we actually figured out that if you want to calculate the electron current, there's another way to calculate it. It's the number density of that particular substance. So for like copper, it's 8.5 times 10 to the 28 electrons per cubic meter. Okay. And then the cross-sectional area of that particular wire. So for example, on this wire, right, this will be the area A. This will be, whatever R is, right? The area of that is pi r squared, right? Times the drift velocity. How fast is the thing moving? Okay. And that's the equation we ended up with yesterday. So we're going to just do a quick example of that just to remind us how this equation works, right? So in this little example from the first thing in the chapter, right? Let's try to calculate what is the electron current, right, in a 2 millimeter diameter copper wire. It's pretty thin wire, so, right, but pretty reasonable. If the drift velocity of the electrons, if the drift velocity doesn't say electrons, is 1 times 10 to the negative 4 meters per second. Okay, so it doesn't seem like we're given it all the information we need, but there is actually a little bit more than what meets the eye here, right? So the diameter here, right, let's just call that capital D, right, is 2 times 10 to the negative 3 meters, right? I just convert right away to SI units. That allows me to figure out what the radius of the wire is, right? It's 1 times 10 to the negative 3 meter. Then that gives us the area, the cross-sectional area of that wire, right? Because that's just pi r squared. So pi times 1 times 10 to the negative 3. Oops. Can't write it all. Okay. This will be meters square, right? So that's going to be 3.14 times 10 to the negative 6 square meters. Okay. So right away we got this variable. The drift velocity is given to us, okay, 1.0 times 10 to the negative 4, and that's already given to us in SI units, so nice, right? What about the density of electrons in our little, what is the density of electrons? Is there any information that was given in the problem that I didn't read? Doesn't look like there's a number. Anyone? We know it's copper, right? And since we know it's copper, we go up to this table up here, and we just look up, well, the number density of electrons in copper is 8.5 times 10 to the 28. So we go back down here, so we can actually write 8.5 times 10 to the positive 28. And this will be in electrons per, so be a little careful, this is the units of number, okay? I'm just going to put a 1 there so we don't mistake it for like, charge of an electron or something like that. So this is the number of electrons per cubic meter, okay? Okay, so that's why the numerator is just a 1, okay? So IE is just the product of all these things multiplied together, 28. I'm going to, since it's the first time we're dealing with this, I'm going to also write in the units so we know that it'll all come out correctly, hopefully. Okay. So the number, the area is 3.14 times 10 to the negative 6 meters squared, okay? And then the drift velocity, right, is 1 times 10 to the negative 4, and this will be in meters per second, okay? Okay, the idea is that this will be the number of electrons per second, so it should have units of 1/2, right? So let's check that first, okay? So a meter squared here cancels out with 2 factors of meters here. 1 factor cancels out with the last one. And the only remaining units is actually 1/2, right? So that's nice, okay? So let's multiply all these big numbers and tiny numbers together times 3.14 10 to the negative 6 times 1e negative 4. Okay. So the number of electrons traveling through this is 2.7 times 10 to the 19 electrons per second. So electrons are little tiny things, right? So therefore, a lot of them are going to be moving around. Okay? Okay. Eventually, what we're going to do is we're going to convert this to another unit called just regular current as opposed to electron current. We're going to see, how many coulombs per second will be moving around. Okay. So before we move on from this, idea of electron current, right? This example told us that electron current, the drift velocity, right? How fast the electrons are moving across my little wire, right? Is 10 to the minus 4 meters per second, right? And I think yesterday we calculated it will take like 2 hours for an electron to go along a 1 meter long wire, right? And that doesn't seem to make sense, right? Because if I turn on, well, when we used to have light switches here, when we turn on the light switches, right, the lights instantly turn on, right? It doesn't take like 3 hours for the lights to turn on, right? So what we're going to do is kind of look at this discharging capacitor situation and see if we can figure out why, it seems like electricity works instantaneously even though the electrons are moving very slowly. Okay? I have a little thing in my mask. Tickling. Yeah, it's just my hair. Sorry. Okay, so we're going to set up this little example here just to illustrate the process, right? So let's say we have a capacitor that's been charged, right? It's one of those that we played around with yesterday, okay? It's fully charged, so the positive plate will have positive 16 nanocoulombs. So therefore, the negative plate will have equal and opposite the charge, right? Remember, the two sides are going to be exactly equal and opposite each other, right? Because any more charge here, it will just kind of pull more electrons out to here in order to equalize it. And let's say we're going to connect this wire, these two sides of the capacitors with this wire. And then what happens is that if you actually did that in real life, it's basically like shorting a little circuit. Imagine you just plugging 2 wires into your wall jack. You're going to see a big spark. Okay? So that means these charges move from the negative end of the capacitor to the positive end very fast somehow, right? But I just told you that the electron is going to take, like 2 hours to get there, right? So why isn't there like a 2 hours delay before the spark happens? Okay? Okay. In fact, if you calculate the amount of time for the electrons to travel along this wire, it's going to be 2,000 seconds, okay? So I think that's about an hour. Any thoughts? Let's just think about this a little bit. Why is that the case?
Because there's like a lot of electrons.
A lot of electrons where?
Like in there, it's not just one moving around, it's all of them moving
Right.
around.
So remember the idea of a conductor. Matthew, you have a comment also?
Kind of like an incompressible fluid, like water.
It's kind of like that. Yeah, you can think about it like that also. So you both have some good points, right? Remember that the original, when we start, like I think the first chapter, when we talk about conductors, right, or any material, right? Right. Let's say if I have a conductor and I say, oh, the conductor is neutral, Does that mean there's no electrons in there? Right? That just means for every electron, I'm going to draw too many as usual, right? There's a positive charge offsetting it, right? So that means, let's say if I push one extra electron into here, what's going to happen is that that one extra electron is going to push its neighbor over, and that's going to push its neighbor over, and it's going to push its neighbor over, it's going to push its neighbor over, right? And what happened is that basically at the speed of light, okay, at the speed of light, the electron will actually come out on the other side, right? That's why when you connect two ends of a wire, short circuit a wire together, that's, you know, a circuit that's charged, you basically all of that happened, you know, basically instantaneously because the speed of light travels fairly fast, right? 300 million meters per second, okay? So that's sort of the idea. I think I have a better picture of it, right? So I think your analogy of an incompressible fluid is pretty good also, where, you know, when you open a faucet, right, you're not getting the water from, where do we buy water from anyway? TID, right? I think it's TID. You're not getting the water from the tank in TID. You're getting actually the water in the pipe that's almost right next to your faucet, right? So you have a big, so TID has this big tank of water, right? And then there's some pipes that goes towards you, and then your faucet is like right here, right? It's your little knob, right? Right? But when you open this knob, right, you're not getting the water directly out of here. You're actually getting the water, right, that's already filled up in the pipe, right, all the way up to the knob, right? As soon as you open this knob, you're actually getting this little puddle of water, right? Okay? So that's why the water comes out instantaneously when you open the valve versus, you know, waiting for the water to go, you know, all around Turlock to get to you. Another analogy is that, you know, pretend, so this is, I grew up in LA, so so we deal with this all the time, where imagine like a traffic situation where, you know, let's say you're trying to go on whatever this freeway is, right? Okay? And if, you know, even though the cars are moving very slowly, you know, the velocity of the car is small, right? All the way on the other end of the freeway, there's always cars coming out, okay? So that's a similar analogy to it, okay? So either whatever you want to think about faucets, or you want to think about actually what's physically happening, right? Okay, where does it go? Physically happening is actually one electron enters into the one side of the conductor and actually pushes its neighbor over and over and over, and then that force basically travels at the speed of light to the other side of the conductor. So therefore, the signal from, you know, you flipping a switch on a light in a room actually travel basically at the speed of light to the light itself. Okay, so you're not waiting for that particular electrons to arrive. You're forcing one extra electron on the other side of the conductor to jump off the cliff. Okay. Okay, so that's a good little discussion about that. Let's see. Oh, and I think I kind of ruined the stop to think question. Okay, sorry about that. Okay, so now that we have a little bit of understanding of what a current is, well, what an electron current is, we haven't really talked about the non-electron current because we're going to have to do a sign correction there. Okay, right? Electrons, all these electrons are bouncing around the nucleus of the conductor. Let's just go back to this picture, right? Right, where the book has a much better picture than I do, where, right, you have electrons that's trying to get through all the positively charged nucleus of your conductor, right? So let's say this is the big old conductor, okay? What happened is that if you apply, right, normally this electron will just keep bouncing around in random direction, and it's equally probable for the electrons to come out on this side and as it is to come out on that side, right? And when you have 10 to the, you know, 28 electrons bouncing around, right, those charges are actually going to balance each other out. They're not going to, you're not going to get a net current to the left or to the right, right? So what happened is that if you apply a force to these electrons, right, and since electrons are charged, we can apply the electric force, right? The electric force is just the charge of whatever you're talking about, times and some sort of electric field that you created, okay? So what happens if you do this is that if you apply an electric field, and why is the electric field pointing to the left instead of to the right? Once again, which way should the, Alan? Right. Right, since we're dealing with electrons, right, if we want the electrons to move from the left to the right, we actually want an electric field in the opposite direction, right? Because the electrons are oppositely charged, right? The charge of an electron is negative 1.6 times 10 to the negative 19 coulomb, okay? So if you apply an electric field inside this conductor, what's going to happen is that instead of bouncing in random directions, there'll be a tendency to kind of go towards the right. It's still bouncing around crazy like a ping pong ball, you know, on that little fair game that I talked about last time. But there will be a net displacement to the right, right? This net displacement to the right over time, right? Net delta x over time. This is the drift velocity that we just talked about, okay? So how do we establish a drift velocity like that, okay? Because remember, one of the things we talked about last chapter, is that inside a conductor, right, under electrostatic equilibrium, what's the electric field inside a conductor? It's zero, yeah, right? Remember this was the Gaussian thing that we talked about in actually chapter 24, right? The reason is that if you, since in a conductor, charges are free to move around, right? The positive charges are going to be trying to get as far away from each other as possible, right? The example I said is like if everybody was, you know, just play tennis right now, all of you guys will be sitting as far apart from each other as possible, right? Everyone will be repellent to each other, okay? So therefore, the electric field inside conductors is going to be zero. But this is in the case of electrostatic equilibrium, meaning the charges are not moving around anymore, okay? So what happens is that if, let's do this little drawing here, right? If we had a capacitor that's been fully charged, okay, and we're gonna do the same wire as that we did last time, but then not connect the wire yet, okay? We're gonna put a little switch there, and then we'll see what happens, okay? What happens is that all the charges will reside on the surface of the conductor, just as Gauss's law told us, okay? But the electric field is inside that conductor is zero, so nothing is moving, right? So once we connect the two halves, right, through a wire, the positive plate gets connected. You kind of stick those two wires together. What happened is that now, okay, right, the positive charges, let me just go back up to this drawing. Once you make this connection between the two, this positive charge is going to hop over to the left, and then this negative charge is going to hop over to the left. Right now, there's no gap. Right now, they're free to move, right? Once they start moving, okay, once they start moving, right, a positive charge is going to offset a negative charge, right? So if you have one proton, one electron, the net charge is actually zero. So they basically just imagine the charges kind of like annihilating each other, right? Not the mass themselves, but the charge themselves, they're kind of neutralizing each other. Okay? So this keeps happening at this point right here. Neutralize, 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 right? This causes, you know, the positive charge on this part of the wire to get depleted, right? As well as the negative charge on this part of the wire. They're getting used up. Does that make sense? Right? Okay? So what happened is that, well, then there's a lack of positive charge here, but then there's a big supply of positive charge along the wire all the way out to the capacitor plate, right? So what happened is that now the positive charge is going to start moving along this wire to kind of replenish it. Okay? So, so that's how a current gets established. Okay? And this distribution of charge, so you see there's more, like from up here, right? There's more positive charge here, and there's fewer positive charge here, right? Remember, electric field goes from positive charge to lower charge, right? So there's actually an electric field pointing along the wire. I actually wish they actually draw a wire that's easier to draw, but does that make sense? Right? All right. Let me just do a simpler example. Right? This is less realistic, right? So let's say you have a bunch of, red, bunch of positive charge here, right? A lot of positive charge on this end, fewer, and then fewer, right? Right? These electric fields, right? There's going to be a strong electric field here, a weaker electric field here, and almost no electric field here, right? Therefore, the net electric field is going to be pointing, kind of pulling all of these positive charges to the right, okay? Just because there's an imbalance of charge at that point, okay? But what's going to happen, as we saw within like, a microsecond, right? All these charges are going to kind of balance each other and get the spark, okay? So the charges are actually going to neutralize each other eventually, okay? But that's how you establish a current in a conductor, okay? So what we're going to do, we're going to look at this idea where, right, the charges are still residing on the surface of the conductor, okay? Remember looking up here, right? They're still on the surface. They're still not inside in the core of the conductor, but they kind of arrange themselves as kind of like rings, like this in a circular wire, right? Where when you have a more positively, there's more positive charge here, it creates a net electric field to the right. And if you have more negative charge here than here, between these two rings, right, there's a net electric field going to the right also. So they all kind of push in the same direction. Okay? So, and there's a couple of examples of this. I just want to finish up this section before we jump into the worksheet. So this is how we establish a current, and this is our first introduction to this idea. Instead of electrostatics, right, we're going to be doing electrodynamics, okay, meaning the charges are going to be moving around instead of staying still, okay? And we can quantify the magnitude of this just by applying Newton's law, okay, right? Remember, Newton's law tells us that, well, the acceleration of something is just the force over the mass. Well, the force on an electron in a conductor with an electric field E, right, is that charge of the electron times the electric field, okay? And now if we go back, all the way back to chapter 2 with our kinematic equations, right, if we have a constant acceleration, right, we can actually derive the velocity of our electrons, right? The velocity of electrons, right, is v equal to v naught times the acceleration times delta t. Acceleration is up here, right? So the acceleration times delta t is this term here, okay? And therefore, now we can actually say, well, if we average the velocity of the electrons in the x direction, let's say we're just dealing with positive x direction motion, right? That's going to be just the average amount of time that particular electron is spent being accelerated. Remember, the electron is bouncing around inside the conductor, right? So when it's bouncing, when it hits the nucleus, right, the electric field is not accelerating it. It's only when it's flying around between all the positive charge, right? That's when it's accelerating, right? Right. So this is known as the flight time of the electron, okay? So when you average this delta T, it turns into this, I think there's a technical word for it. It's the mean time between collision. That's what this tau turns into. Okay? So this is yet another way to calculate the drift velocity of our little electrons. If we apply some electric field E, right, the charge of electron is given to you, right, the mass of electron is also given, okay? So therefore, what we can do is then we can make this equation even more complicated, right, by plugging in what the drift velocity is, okay, in terms of electric field, okay? So the electron current is now this long, complicated equation, but the thing I want you to take away is that it is proportional to the electric field. The stronger the electric field, the faster the electron will be moving around. Okay? Let's see. I don't have time to get to the... I'm trying to get through enough material to talk about the stuff that's going to be in the worksheet. Okay, so that's how you calculate the electron current. I think the next section is what we need to get through in order to do the worksheet today. Okay? So far we talked about electron current. Remember, the electron current is just how many electrons are moving per unit of time. So we're trying to keep track of, this electron as it's moving around in the conductor, right? Okay. So now we're gonna change it. So we're gonna be quantifying things in terms of SI units instead, okay? Because this current here, right, is the number of electrons per unit time. What we're actually interested in is actually how much charge are moving per unit of time. Okay, so how do we go from electron current to what, now the terminology is just the regular current, okay? So this is the electron current, and this is just called current, okay? And the units for a current is a coulomb per second, and since it's used so much, there's another term for it named after this guy, ampere. 1 amp is the units for a current, but it's the same thing, 1 amp. It's the same thing as 1 coulomb per second, okay? So all we have to do to convert the electron current to regular current is to multiply the electron current times the charge of the electron, right? Right? Because 1 electron, right, let's say I have 1 electron that's, bouncing around, right? This is carrying 1 charge of an electron, 1 times 10 to the negative 19 with a negative sign. That's how many coulombs of charge that will be carried across that metal conductor, right, if it moves across, right? So if we multiply by the charge of electron, right, so this E, right, is not 2.718, right? This signifies the charge of the electron. Okay, so be careful with this E, okay? So with that, what we can do is now we have our little proper definition of what a current is in SI units. So this is the equation that you're going to use in SI units. Okay? Okay. We're going to complicate things a little bit more because it's going to be useful when we're dealing with wires of different sizes. Okay? We're going to try to cover this thing called current density. Meaning, current density is just like any other density that you can think about. It's basically the current divided by some sort of volume, area, or length. Okay? Since on a wire, right, the current, right, is going across some cross-sectional area, right? Therefore, the current density we're interested in is the current divided by the area. In fact, if we just take this equation up here, divide both sides by the area, we basically divide out the area on the right-hand side, okay? So the current density is just the electron density on that particular metal, the charge of an electron, times the drift velocity of those electrons. Okay? For example, for copper, right, the maximum current density is about 500 amps per square centimeter. Okay? So that means if you have a wire that's approximately a square centimeter, which is a little bit, maybe a little bit bigger than this, it can only carry 500 amps. Okay, 500 amps is actually quite a bit, so that's why generally a lot of wires are smaller than this. Okay, and so we can actually calculate using this equation here, we can either calculate the current density, the electron density is always just going to be given to you because you know what type of metal it is. Okay, and if you know the charge of an electron and you know the drift velocity, you can actually calculate, the other three variables, let's say. Okay, so do I have time? Yeah, I'm going to do the examples for this next time so we can actually jump into the worksheets. There's one thing that I want to talk about before we leave, before I jump into the worksheet, is that we can talk about, now that we have this idea of current, right, in SI units instead of electron current, but you can still think about it as electron current, okay? The weird thing about electron current is that, right, regular current is assuming that these charges are positive moving along the wire. Electron currents are actually electrons going opposite direction, okay? Just be a little careful about that. But hopefully we can introduce this concept and let you guys work on your worksheet. So let's say you have some current on some wire. So this orange blob, just imagine it's like a straw with some current going through it. Okay. What happened is that, well, what if there's a split in that wire? Okay. This is called a junction, right? What happened is that, well, there's going to be some current that goes on this junction, some current that goes in this junction, right? It's kind of like a split in the road. Okay. So therefore, right, let's say we have some current coming in, and it splits into current 1, and current number 2, right? The relationship between them has to be that whatever the current coming in is going to be current 1 plus current 2, right? Right, hopefully that makes sense. And we're going to call this, right, I out 1 plus I out 2, right? Because the idea is that in a junction, relative to this junction, this current is coming in, these two currents are coming out. Okay. Similarly, if you have the backwards version of this, what happens is that you have two currents coming in and one current coming out, right? The sum of the current that's coming in is going to be the sum of the current that's going out. Okay. Right. Okay. And therefore, this is the first kind of electrodynamic law we learn about. This is known as Kirchhoff's junction law, or another way to call this is actually Kirchhoff's current law, because it has to do with current. But all it tells you is that sum of the current that's going into a junction has to equal to the sum of the current that's going out. Okay? Yeah, so we only have 10 minutes. So let's see if we can jump in and start the worksheet today. Maybe we'll finish it up tomorrow, okay? Everyone has a little popsicle stick, and then we can go to our groups.